I'm going to speak a little bit about the CXL Consortium itself, how it was formed, and what the output is, basically the specification. As you probably already know, CXL Consortium has 15 board members, 9 promoter companies, several contributor companies, and the board of directors is complete now with 15 board members. As you probably know, on the name list here, Rambus, Larry Carr from Rambus is the re-emergent director to the board of directors with Rambus. And today, this morning, as part of the board of director meeting, Larry got elected as the president of the CXL Consortium. So congratulations to Larry carrying the torch forward. So CXL has demonstrated itself as a de facto industry standard protocol for interconnect, for high-speed, low-latency interconnect. During that journey, Gen Z and OpenCAPI decided to move their assets to CXL, and those specifications are available for CXL team members to incorporate in new features. So let me just go through what CXL technology is and give you a little tidbits and some of the interesting things about CXL 3.0. A lot of the work is normally done as part of CXL Consortium within work groups, board of directors, and then there are 2 major elements: technical task force and marketing work group report directly to the board of directors, but they have work streams and work groups that are very active. Normally what happens is use cases are identified, and responses to use cases turn into proposals from different company members, different contributors, and they get debated, and eventually a solution is invented or emerges from those discussions and gets put into the specifications. And most of the early slides that I will share with you is an output of the technical task force and different technical work groups. At the end of the presentations, I also have some reports from the marketing work group based on the work that's been done in the industry already. So the concept of CXL started from earlier interconnects in the past. Different interconnects were going in different directions. The promoter companies got together and eventually agreed to produce the same specification, one specification for all to use. In March 2019, for example, CXL 1.0 was contributed. Then different companies got together with 15 member companies. CXL 1.0 with the compliance chapter was released. And in November 2020 is when CXL 2.0 was released. Just recently in August, as part of the Flash Memory Summit, CXL 3.0 was released. Now we have over 240 member companies. That's a great testimony to how useful CXL technology will be. So in a nutshell, CXL has a very simple approach. First, do no harm. Based on PCIe, established PCIe techniques. One of the protocols used, CXL.io, is basically similar to what PCIe does. It is participating in bus and device enumeration, configuration. It is participating in DMA, moving memory, similar to what DMA engines do as part of PCIe. But then CXL brings in 2 high high-speed, low-latency latencycy protocols as well, CXL.Mem and CXL.Cache. They use, all three protocols use the same physical layer, physical link layer, but there are three different protocols for different use cases I will cover in a minute. For the CXL.Mem, CXL.Cache, the expectations are the data gets moved within 200 nanoseconds as compared to bulk movement by CXL.io that might take longer, but it also is capable of moving larger bulk of memory. Another aspect of CXL is the fact that to enable devices to emerge faster, put the burden on the host side. So on the cache coherence protocols, the host does most of the work. So in that model, it is asymmetric. Most of the work is done by the host, so the devices can be simpler. When we put all of this together, using the CXL.Mem, CXL.Cache, we create a converged memory. Within a converged memory, you can imagine that a piece of software can run on the host, and without much work, it can be ported to be run on an accelerator, and they can share the same regions of memory, either as part of the host memory or as part of the device memory. So that is an efficiency gain, reducing the amount of time and power that it takes to move data for applications that require accelerators such as GPUs. So thinking about then three different protocols, as I mentioned, CXL.io, CXL.Mem, and CXL.Cache, then we can think of three types of devices. Simply, we call them type 1, type 2, and type 3. So a type 1 device is the one that implements CXL.Cache. A good example of that might be a NIC, or maybe even a storage controller that would like to initiate cycles towards the host memory. So CXL.Cache is used by the device to reach out into host memory and in a cache coherence model, and hardware takes care of cache coherence between the two devices. A CXL.Mem only device is a type 3 device. It behaves like a memory. Every one of these devices will still have to implement CXL.io for programming, for responding to interrupts or generating interrupts. But a CXL type 3 device implements CXL.Mem, and it receives CXL.Mem cycles, whereas a CPU initiates CXL.Mem. So distinction, CXL device could initiate CXL.Cache, such as a type 1 device, and the processor initiates a CXL.Mem destined for a type 3 device. Now you can imagine a device can be an accelerator that has local memory also. That is the type 2 device that implements all three protocols, .io for programming and moving bulk data, .cache for cache coherency cycles initiated by the device, and .mem for the device to receive memory cycles from the host CPU, for example. Now, if you remember, CXL 2.0 introduced four major features. It created a layer of switching, one layer of switching for fan-out. A host might have one or many ports. On each port, you could have a switch, and that switch can have multiple downstream ports. And therefore, even with the CXL 2.0, one can create a large ensemble of devices to be connected in a fan-out fashion to the host. Some of these devices might be persistent memory type devices. To enable persistent memory, it is important for all of the queues to be flushed into the persistent store. Because of that, it was important to have a global persistent flush concept created. That was a major use case. Once devices are farther away from the CPU, it is important for them to be secure. So encryption model was created as part of IDE protocol, similar to what PCIe had done as well. So when you put them all together, one can create a memory pool system as well with this, with the introduction of a multi-logical device. The diagram is showing a single logical device, SLD. All of that device can be dedicated to one host. And this model is dedicated to host 1. A device can subdivide its memory segments into multiple regions. Each region can be dedicated to a different processor. So that is a multi-logical device. A switch, a CXL 2.0 switch, might have multiple multi-logical devices or multiple single logical devices, SLD devices connected to it. CXL 3.0 added much more capabilities, mostly around fabric capabilities, enhanced switching capabilities. I'll go over them one at a time. And then describe multi-headed devices that, similar to MLDs, could be managed using CXL Fabric Manager, and introduce topics suitable for near memory computing. One of the special items, the special capabilities for CXL 3.0 was its bitrate. Doubling the bitrate from 32 gigatransfer per second to 64 transfer per second using PAM4 based on the physical layer of PCIe Gen 6. On the enhanced switching capabilities, one important factor is the capability of a peer-to-peer communication between an accelerator, for example, and a memory device, or accelerator to a NIC or a storage device. That was a special capability that CXL 3.0 provided. As part of switch fan-out, CXL 2.0 allowed only one .Cache device to be connected to a switch, but it did allow multiple .Mem devices to be fanned out. For CXL 3.0, that capability now exists for multiple .Cache devices or multiple .Mem devices to be connected. CXL 3.0 is not limited to only one layer of switching. Switches can be cascaded. I have a couple of diagrams to show that. On the fabric capabilities, when you can interconnect multiple switches, you can imagine different fabric topologies which allow compute disaggregation to be enabled. And once compute disaggregation is possible, then one can put them all back together and create a composable memory system, for example, out of disaggregated units. For fabric devices, fabric switches, and fabric connected devices to work well, a layer of management is necessary. So CXL Fabric Manager enhancements to CXL Fabric Manager as part of CXL 3.0 specifications to enhance the capability. In all of this, CXL is taking pride in being fully backward compatible, as CXL 3.0 specification allows CXL 1.1, 1.0, 2.0, or 3.0 all be plugged into the same fabric, same switch. Some switches may or may not provide all capabilities. It is allowed. That provides investment protection. If somebody has already started designing and productizing a particular silicon solution, it is nice for it to be backward and forward compatible with the spec.
With the backward compatibility, does everything revert to the capabilities of the oldest device on the chain, or does each device have its own independent connection where one runs at 1.0, another can run at 2.0, et cetera?
All of those are possible. CXL provides a number of mandatory requirements. So if a device claims to be CXL 2.0 or 3.0, has to follow certain mandatory feature sets, but there are a number of optional features. A device manufacturer might choose certain CXL 2.0 features, certain but not all CXL 3.0 features. In all those cases, the capability bits within the device will report on what that device is capable of doing. When during the link negotiation, a root port, either directly connected to a processor or a downstream port of a switch, when they connect to a device as a target device, they negotiate on the capability bits, and they select the bit rate, select the width, select the capabilities, and select the type of protocol they run, .io, .mem, .cache, a number of other features, all within capability bits. Piece of firmware, as part of the device discovery and enumeration, goes and reads all of the capability bits, and based on those bits enables other features. So a combination of what the device has implemented and what the firmware has enabled creates a full set of one particular device is being used in one environment or another. A device might be capable of running high-level features, but if the firmware didn't implement it, or if the driver or some piece of software chose not to enable it, they can turn them off and not use it.
Is this an end-to-end negotiation, or is this a port-to-port negotiation?
It starts on the link, so it is a point-to-point, port-to-port negotiation. But if there's a large system, the entire system has to work for the whole end-to-end to have a particular feature.
Right. So if it is a port-to-port negotiation, that also means that you potentially run into cases where devices need to be able to buffer.
The devices, depending on the feature and how much buffer or queuing they need to adjust for that. Yes.
Well, I mean, does that become another capability that needs to be listed on how much buffering capability they have?
Again, on every optional feature, there is a capability bit, and some of these optional feature might have ranges.
Okay.
So there are registers that report on the range of features that they have. Size, dimensions, latencies, those might be part of those type of capabilities.
Well, to build on this question, is it then up to the software to show me what is enabled? I'm thinking about if I have different generations of CXL devices, one that supports encryption and one that does not. For me, it would be important to know what is actually has been negotiated. And would that be then up to the software to show me what is happening on that link, what has been negotiated, what is active, what's not active?
You're correct. There are multiple layers. The device, the spec has to allow it first. Right. And the device has to implement it. Mm-hmm. And then firmware needs to discover it and enable it. Then, depending on the end-to-end that we just talked about, it might not be feasible or desirable to enable everything along the way. So there might be some choices, judicious choices by firmware or the software that eventually lands on it to enable certain features. Now, if the question is, will the device do it or not? There's one answer, but will the system implement the entire chain to enable that particular feature is done by the high-level software.
Right, and that high-level software would then list me as, let's say, as an operator, sysadmin, what has been negotiated.
You can get reports on that, and software developers will have tools mm-hmm. to, based on reading all the capability bits yep. in different locations, to report back what has already been enabled and what's actually running.
Because it clearly would be very important if all of a sudden my encryption is turned off.
Sure.
know about this.
Yes, exactly.
Okay.
Good question.
And some features are not in the spec, right? It's okay for devices, for example, to implement their own way of doing things and their own capabilities and features and report those. Is that integrated with CXL or is that just parallel?
Your statement started by saying certain things are not spec'd.
Yeah.
If things are not spec'd, then there's no standard CXL way of discovering them. There are a number of vendor-defined features that are there, and they are vendor-defined. You have to have some sort of a driver and some sort of a vendor-specific understanding of what those things are. As you guys know, when we are as part of a group of people, let's call it a consortium, building something, specification is the type of things to limit you from doing certain things, to get into trouble. So we have tried very hard not to limit innovation. So we'd like everything to be possible, but then for interoperability, certain things they need to be aligned. So the point A connected to point B, they know how to negotiate. But we don't want to stop people from inventing things and moving the technology forward. Therefore, there are a number of vendor-specific features that they can implement.
Can those actually be grouped together like in SCSI with the vendor-defined inquiry page?
There are specific methods to query vendor-specific items.
Okay.
And then you get a bit list or a registered dump, and you have to interpret what those things mean. And it's very likely a device of that capability will have a device driver to do that interpretation for you.
Okay.
Very good. So one distinction I wanted to draw here is the definition of a tree hierarchy. Everybody's perhaps familiar what PCIe does. Defines a tree structure, and if you have a host CPU, such as host number 2 here, wants to reach device 1, device 2, device 5, and device 6, one can identify a tree structure for that. And if device 1 wants to talk to host 2, it's very simple, straightforward. But if a device wants to reach a neighboring device, through the tree structure, it has to go all the way up to the root of the tree to the host and then come back. So PCIe allows that. Peer-to-peer can be done through the host, but you can imagine that that will create a bottleneck on the link that's connected to the host. So again, it can be done, but it creates that dependency and bottleneck. With CXL 3.0, it was highly desirable to have a faster method, a non-blocking method, a method without inherent bottleneck by the spec. So there might be bottlenecks within the devices. Hey, that's part of the device implementation, but the spec allows for device-to-device, peer-to-peer communication within a switch hierarchy, not to have to rely on the host link. So that's a major addition for CXL 3.0 to support peer-to-peer. Along with that, 2 other important features that were implemented and developed were unordered I/O for more efficient data movement, that ordering rules are maintained by the source, not by the fabric. And then back invalidate channel that was created, so for caching and snooping that needs to be done for cache coherence, maintaining cache coherence in hardware to support peer-to-peer.
And which devices would have peer-to-peer access? What would be a use case for that?
A GPU wanting to go to a NIC, a GPU wanting to expand its memory footprint from all of its local to all of the memory that might be on the fabric. Peer-to-peer connection. So the devices, device 3 might be a memory device. It could be MLD or shared memory. I have some diagrams for that as well. Right. So this might be an answer to some of your questions. A device we talked about could be a single logical device, all of its memory being dedicated to one host, or it could be a multi-logical device, part of it be dedicated to one host, another part be dedicated to a different host. A variation of that for CXL 3.0 is a concept of sharing. So a region of memory can be assigned and bound to more than one host. That allows memory sharing. Because of the existence of such a shared region, then the two hosts can do host-to-host communication using that shared memory. So a slide before, we talked about peer-to-peer communication for end devices, but this one illustrates a method for host-to-host communication through that shared memory. And the back invalidate channel is necessary to implement shared memory as well. Now, when we put things together, memory pooling and memory sharing, we can imagine that there is a switch, multiple devices connected to it. Each device is capable of subdividing itself. Portion of those devices would like to share a region with all hosts, portion of them being dedicated. All of that is possible. And in that model, earlier discussions, people talked about memory come and go, dynamic capacity device is a specification for a device memory regions to grow or shrink, communicating that one to the memory management unit running on the host.
Can you really define a host for me? Because this is very foreign to traditional, like a server architecture where there is a box with a board and it has chips on it. There's a processor and there's stuff, right? Right. But now you're talking about disaggregating everything, but we're still addressing things as hosts.
The word host, you're very good. Thank you for asking that question. In this model, an example like this, host is really a CPU.
Okay.
A CPU, host CPU or host operating system. Host operating system, a hypervisor, host as compared to a VM or a guest operating system, a host operating system running on a host CPU. That is the terminology we're using here when we say a host. It does not mean the entire ensemble of networking and storage and memory and everything else. And that's how we are disaggregating things. Host CPU, different from the accelerator processing element. They're not connected to each other, they're farther apart. Host CPU might have local memory, but it might be operating off of CXL memory, disaggregated. But host in this model is the one with the root port that initiates .mem cycles.
And so real world examples of, say, a big server with multi-cores, it would still be an OS running on a single processor that would have the, what was the term you just used, where accelerators elsewhere to use, right, as part of the fabric.
Another very good distinction, in this model, when we are saying host, it could be there could be a host operating system running on one CPU or running on more than one CPU. So it could be a symmetric multiprocessing. The whole ensemble could be the compute element, general purpose compute element, a number of CPUs. It's still not a complete system because it doesn't have its NIC and storage. The NIC and storage is connected through CXL fabric, for example. Now, a combination of all, in this diagram, for example, you can imagine host 1 being bound to a portion of device 4 and a portion of device 1. So you can draw a line around all of those. So we disaggregate first, and then we compose them using software constructs that we talked about earlier during some of the talks. That creates now a composable system. Good questions.
That makes it a lot clearer now. Thank you.
Thank you. Yes, apologize if the word host was not clear earlier. I should have been more.
Well, it's a generic term that we use for everything.
Right.
I mean, I say host when I'm talking about my phone on my phone network.
Right. True. True. Okay. Another aspect of a switch layer for CXL 3.0 is the fact that Now more than one layer. We could have multiple layers, either for fan out or for cascading. And once we do that, you can immediately see that certain capabilities will be possible. You can imagine a spine and leaf system. You could have a switch box, as this diagram is trying to show, a switch box that implements your spine layer. And then you can have a number of appliances. Each one of those appliances might have a switch in it and a bunch of devices. One of them might be dedicated to a number of NICs. One of them might be dedicated to a number of SSDs. One of them might be a JBOM, as earlier discussions, could be all memory. All of those can still be a couple of hops away from each other, bouncing back and forth through the spine. So leaf and spine model can be done using CXL switch fabric with 3.0 spec.
I have a question just on the leaf and spine. If we were doing leaf and spine from a networking standpoint, would we be using BGP or ECMP, BGP multipath routing to try and maximize throughput? Is it that kind of approach where different connections are split across ports to saturate as much upload download bandwidth as possible, or is it closer to spanning tree where either all traffic's going out one or per device going out another?
Right.
How does that work?
With CXL specifications, the successive generation, we're introducing those topics one at a time. In this model, first we didn't have any switch. Then we had one layer of switch. Now we have multiple layer of switches. As providing aggregate bandwidth, we do have interleaving. So you can have a device that has multiple ports, a CPU, for example, with multiple ports. It can interleave across CXL links. Each link can go to a different switch, and downstream from that, there might be multiple devices. So a CPU can have an aggregate bandwidth of all the layers that it has. So that's for aggregating bandwidth. But you're also talking about multipathing. The multipathing is a concept that a lot of CXL fabric people, we have a dedicated fabric work group, know about it, they desire to have it, but it is not in this particular spec yet. So once we kind of build crawl, walk, run systems, these things, you can imagine that they will come.
I wouldn't expect it to be in the minimum viable product, bringing in fabrics, but it's just it's interesting to know how it works because it's a design consideration.
Right. Yes. Please dream big, and we will dream big. We have high visions, and we have multiple goals. Step by step, we'll get there. I can summarize on the technical aspects. I have a chart to show all of the CXL features in a minute, but the call to action is the one that I'd like to call your attention to. Please participate. The CXL 3.0 is out there. When people want to design something, you don't have to wait to have everything. You can, if you have a CXL 2.0, it is interoperable with a device that is a switch that's a 1.1. It is interoperable for a future CXL switch that supports 3.0. So don't necessarily wait for everything to be there to start. So you can start. Starting is good. And then come and join and participate in identifying use cases, make proposals, how to solve and implement use cases, and then help implement them, provide feedback. And also participate in any kind of a POC or reference designs. But an hour ago, we talked about a very good innovation. Memberge is talking about building a reference design. Participate in those kind of activities. We need hardware systems to be there so software guys can implement to them and learn, provide feedback, and eventually make these systems more robust. Feature summary from a technical aspect, you can see a superset relationship. CXL 3.0 does everything that CXL 2.0 does, and CXL 2.0 does everything that CXL 1.1 did. We took a crawl, walk, run approach. Immediately after initial release of CXL 1.1, a group of people that got together, imagined certain things, pared it down to only 4 major features so that we could do that within a year or year and a half. We did that. And then later we got more ambitious and created a bigger set for CXL 3.0. CXL 3.0 is released, but people are still working on added features. They're going to come in the form of ECNs and in the form of future specifications as well. So the group is now well-oiled machine. They are working very hard together. That's a very well matched team of number of work streams working in parallel. Come and join. Now, so far I talked about most of the work that the technical task force and the technical working groups have implemented, but the marketing working group is also very active. They have presented in a number of webinars and blogs, and participated in a number of seminars and conferences. This is an example. Many companies presented at Supercomputing 22, and they had parts, they had hardware. It was so exciting. A lot of people got together and showed and competed against each other, but showed what they could do, what they were, what their ambitions were, and what their plan they had to get there. It was a very exciting place to be, packed. There was a lot of interest for CXL. Again, as call to action, please participate, review, provide feedback, solve problems. A number of conferences are planned for this year. They're all part of the CXL announcements and newsletters. We can go to the CXL Consortium website and get a lot of these things and plan for them, get ready. There are a number of resources here. I share that one with the team here as well. If you like, later you can publish them.